So we learned about the function generation for a four-bar mechanism. We talked about the prediction method. We worked on two examples. Now today we would like to synthesize a six-bar mechanism. So ground is first link, second link, third link, fourth link, number 5, and number 6. So we would like to design this mechanism such that it generates this desired task for us. When this input link is moving from first precision point to the second precision point by the angle of 30, this terminal link, which has the angle of gamma, from first precision point to the second precision point is going to move by 60 degrees, and this output link should move from first precision point to the second precision point by 55. And also when it's moving from first precision point to the third one, the first link, this link, input link, by the angle of 45, this terminal link should move by the angle of 90, and the output link should rotate by the angle of 120 degrees. How can we do that? The process is straightforward. First, we consider this four-bar mechanism. This guy, A, B, C, and D. For that mechanism, we know theta 1, 2 is 30, gamma 1, 2 must be 60, theta 1, 3 is 45, gamma 1, 3 should be 90. So all information that we need to design a four-bar mechanism are given for 3 precision points. We can apply prediction method or the other method to size AB, BC, DC, and AD is going to be 1. So you can size and CD, and AD is 1 as always. So after you size this part, you go through the second part. Choose whatever is desired angle for the terminal links for you. Even if you don't want to have a ternary, we can have binary links, but here I assume we have ternary links, so assume one desired angle for this, and this input link is gonna rotate by 60 degrees. The output link should rotate by 55, and the input link, when it's rotating by 90 degrees, the output link should rotate by 120 degrees. So then we synthesize second four-bar mechanism to size D, E, F, and FG, and we are done. Question on this. One group can choose this as a project if they are interested to design a mechanism for this carburetor system, we are going to change the angle. But the idea is design a 6-bar mechanism, one 4-bar here, another 4-bar here, totally 6. When you push the gas pedal by 15 degree, we call it bell crank, I guess. It should rotate by 10.5 angle, and the carburetor should be open by 20 degree. And when you want to speed up, you push more by the angle of 25, it should be open by 17, and the carburetor is going to open by 14, by 40 degree. So you should just follow what I explained on the previous slide to size the required mechanism for this carburetor. Any question on this? So if any group is interested, we can discuss about that and provide the new angles for this carburetor. All right. Let's move on. Least square method. Here, when we started kinematic synthesis, we talked about the precision point. And we looked at this table. The table says if you have a function generation problem, for a 4-bar mechanism, the maximum number of precision points that you might have is 7. So you can have up to 7 precision points to design a 4-bar mechanism such that it generates those precision points for you. But what if we are given by more than 7 precision points? For example, 8 precision points or more. It means we cannot design a 4-bar mechanism such that it goes over 8 or 9 precision points. But we still want to design a mechanism to generate that. So what we can do, we can design a mechanism such that it's going to minimize the error. So if number of precision points are than 7 for 4-bar mechanism, function generation, we are going to have error so we would like to minimize the error on our design. So this method, which is least square synthesis of 4-bar function generation, it's gonna cover that. If you have more than 7 precision points, for example, we would like to generate or design or synthesis a 4-bar mechanism such that it provides this desired correlation between input angle and output angle. When the mechanism is moving from first precision point to second precision point by 10 degrees, the output angle should move by 12. and when it's going from 1 to 3 by 20 degree, the output angle should move by 15. And when it's moving from first precision point to 8th precision point by angle of 70, output angle should move by 40. So you are gonna do this as a homework problem with the same numbers, but we will learn how we can do that. So the idea is, we know that we cannot design a mechanism to go to cover these precision points or tasks. But what we can do is, we do the design such that it's gonna minimize the error. So first of all, we should define the error. What would be the error? How can we define that? So in condensed method equation, we got this: K1 cosine of phi minus K2 cosine of theta I plus K3 equals to cosine of theta I minus phi. If you remember, at that problem we had 3 precision points, and this equation should be satisfied in all 3 precision points. But what if we cannot go over precision point? Then the left side is not going to be the same as the right side in all 8 precision points, or in all 8 desired points that you would like to generate. In that case, this minus this is not going to be 0, and we define that as an error. So error I representing the precision point, or the point that we are talking about that. So EI would be K1 cosine of phi minus K2 cosine of theta I plus K3 minus cosine of theta I minus phi. Error. Good. It's obvious that when we had 3 precision points, the EI was 0. But we are gonna design a mechanism such that in this case 8. Sum of a square of error should be minimized. So I'm gonna design a mechanism such that this summation is minimized. So we would like to minimize this. You might say, why don't we minimize the summation of the error? Can anyone answer this question?
The error can either be positive or negative.
Exactly. The error can be positive and negative, and they cancel out the effect of each other. For example, at the first precision point, you might get error positive 2.1. In second precision point, you might get the error negative 1.5. When you add them up, you will get positive 0.6. But the reality is we don't want to do that, because this is the error, this is the error. We should treat them as a positive. So I can say this, but again, I don't want to deal with the absolute value, because I cannot differentiate that to optimize that. So I introduce the S squared, the summation of the S squared of the error, to get rid of the sign. So it's the reason that I'm going to use this. So we are going to minimize summation of EI squared. This is the EI, so I'm going to square that. I goes from 1 to n, but n is going to be 8 in this example. So I just want to be more general, so I use n. Question so far? So now, if you have a function like this, you want to minimize that, and the variables are k1, k2, and k3. If you have a function and you want to minimize that, what you are going to do, you set the derivative of this function with respect to each variable equals to 0. So if I call it E, which is the total summation of the square of the error, the del of E with respect to K1 must be set equal to 0, del of E with respect to K2 must be 0, and del of E with respect to K3 must be set equal to 0. Good? So look at this. If I want to differentiate this with respect to K1, the only term which has K1 is this guy, and we have S squared here, so it's gonna be summation of I goes from 1 to n, 2 is coming out of parentheses, times K1 cosine of Pi minus K2 cosine of theta I plus K3 minus cosine of theta I minus Phi times derivative of K1, the derivative of this term with respect to K1 is going to be cosine of Phi. So this is for first equation. Second equation is going to be I goes from 1 to n. The only term which has K2 is going to be this, but we have S squared here. Derivative of this with respect to K2 is going to be 2 times the entire of the parentheses multiplied by what would be the derivative of this term, which is negative cosine of theta. So it's going to be 2 K1 cosine of Phi minus K2 cosine of theta I plus K3 minus cosine of theta I minus Phi times negative cosine of theta I, and it's equals to 0. And K3, 2 times this parentheses, derivative of K3 with respect to K3 is 1. So it's going to be summation of I equals to 1 to n, 2 times K1 cosine of Phi minus K2 cosine of theta I plus K3 minus cosine of theta I minus Phi. Any question on this? Good?
So this equation goes with the function with the minimizing the error?
We are minimizing this function, which is the summation of S squared of the error. This is the error. I S squared that, and I add them up in all 8 precision points, or whatever is the number of precision point that you want to generate. And I would like to minimize this summation. How can I minimize a function? I'm going to differentiate with respect to the variables. The variables are K1, K2, K3. To differentiate, set equals to 0. Good? So, 2 is a coefficient. I can divide both sides by 2, so I can cancel out 2 from both sides. These 2 also can be cancelled out. This negative sign from both sides, if you multiply by negative, can be cancelled out. And these 2 also can be cancelled out. So we get you have whatever is the number of angles, precision point that you have here, you find this summation, K1 times cosine of phi1 minus cosine of theta 1 plus K3 minus cosine of theta 1 minus phi1 times cosine of phi1 plus K1 cosine of phi2 minus K2 cosine of theta 2. So we do all the math, we get three equations with three unknowns. The unknowns would be K1, K2, and K3. It's gonna look like this. If you multiply cosine of phi, I will get K1 cosine of phi squared minus K2 cosine of theta I cosine of phi plus K3 cosine of phi minus cosine of theta I minus phi times cosine of phi. So K1 is not varying for different precision point, is coming out of the sigma. So you will get K1 times this minus K2 times this plus K3 times this, and I'm going to move this negative to the other side. It's going to be positive summation of cosine of theta I minus phi cosine of phi I goes from 1 to 1. So summation of cosine of this angle is going to be one number. Summation of this multiplication for all 8 points would be one value. Summation of this guy is going to be one value. And also this side I will get one value. So it's going to be three equations, three unknown, similar to, for instance, a system of equation that we derive is solved for K1, K2, K3. And we recover mechanism dimension. Okay, for these types of the problem, we should start from free choices. You assume theta 1 and phi 1 as suitable free choices. So theta 1, whatever 30. Phi 1 is 150. These are my free choices. Then we are given with theta 1, 2. If we are given by theta 1, 2, I can find theta 2. Theta 2 is theta 1 plus theta 1, 2, which is 40. Phi 2 would be phi 1 plus phi 1, 2. 115 plus 12, 127. Find theta 3, theta 4 up to theta 8, and phi 8. So you have 8 precision points in this case. Put the angles in this system of equations, find the sigmas. You have 8 phi angles, find the summation of cosine squared. You have 8 theta and 8 phi, find this multiplication for 8, add them up, do the same thing for the other coefficients. You get 3 equations, 3 unknowns. Then solve for K1, K2, K3. Once you find the value for them, you can find A, E, and C. If there is any requirement for the mechanical mechanism, suppose you want to have crank rocker. If A, B, C, and D doesn't satisfy the crank rocker condition, you have to come out and change these two, theta 1 and phi 1, and then try again. Any question on this? All right, let me look at problem 2 of the homework. it's asking to apply the least square method that I just covered. The initial, the starting point or the free choices are given 15 and 100. You should do that. It doesn't ask you to have a crank cracker or something like this. You find A, B, C, and D. But the next part is the interesting part, which is asking you to plot phi desired versus and phi design versus the input angle, which is theta. So what you need to do is by this initial point, you find K1, K2, K3. By K1, K2, K3, you can find A, B, and C, and D is 1. So now you have a mechanism, 4-bar mechanism, with A is given, B is given, C is given, and D also is given, which is 1. Now, input angle is theta 1 equals to 15. You go to homework 4 or 5, the code that you have written for a 4-bar mechanism. You plug in input angle theta 1, 15, you will find phi 1, the output angle corresponding to this, and we call it design. So you design this mechanism. So for this theta, it's gonna generate this phi 1 for you. Do the same things for theta 2. Theta 2 is 15 plus theta 1, 2. Theta 1, 2, whatever is the value for theta 1, 2, you have it. For that one also you find phi 2 by using the MATLAB code that you have designed. So you will find 8 design value for phi. What would be the phi 1 for desire? You desire to generate a mechanism such that phi to be 12 plus phi 1, I said 150. 100. Phi 1 is 100. You would like to have phi 1 100, but phi 2 desire is phi 1 plus phi 1 2, which is 12. 112. So you will get 8 value for phi 8. Phi 1 to phi 8. Then plot something like this. Have this angle, this axis as your theta, and this axis as your phi. First, plot phi 1 versus theta 1. Whatever the theta 1 is coming here, what would be phi 1 corresponding to that? Locate that. You will find 8 points. Do the same thing for this. You will find another 8 points. So this is a phi desired and phi design versus theta. And I ask you to compute the error. What is the error? We define the error on this slide. Here. For each point, you have the phi that you generated. You have theta, which is the input angle, so you can find the difference between left side and right side, which is the error. And plot theta versus phi. Is that clear? What I'm asking you. Any question about the homework? Problem number 2. And problem number 1, I think I talked about that yesterday. I'm asking you to write a code, MATLAB code, such that it's solving the example that we did in the class to generate this function for a metering device. The precision points would be the same as the example that we did in class. But we would like to have crank rocker. So the free choices that you pick, it should give the result such that the mechanism is a crank rocker. If it's not, you have to try another set of theta 1 and phi 1. Okay. Problem 3 and 4, you should wait until the color on Monday class and follow this. Any question on this? So I looked at the exam problem, problem 2. It seems there is I missed the length of the links for a inverted slider crank. For some reason, if you look at the exam problem, there is a space left next to the A, B, C, and D, and for some reason it didn't show up on the file that I printed out. So what I'm gonna do, I'm not gonna look at the numerical result. I'm just looking at how did you set up the velocity and acceleration equation based on the parameters. Fair enough? Because it's a mistake that I made, so I'm gonna treat it. But the problem 1 doesn't have any. So I'm gonna finish today's class early. So the due date for the homework would be Friday, December 6th. But we can start working on first 2 problems right now. And make sure that you finish your design as soon as possible, because you have to schedule a time with Jim and the step lab to print out the parts. I sent you what I need for.
I talked to him today. He said there's software that needs to be updated in a 3D printer. So he said it'd probably be done by after break.
After the Thanksgiving, you mean?
Yeah.
So next week we cannot.
Yeah. Right.
Okay.
There's a 3D print lab in this building as well.
We do, but
He said it would take only 15, 20 minutes, but he has to find time to do it, to update, I guess, 3D printer or something.
yeah, I wish we could use this one, but the technician for this 3D printer, I don't know who is running this year, because he left the job a couple of months ago. Do you know who is running this?
I can talk to Jim about step lab tonight. I can also see if he can just give me the link to where to install the software, and I can see if I can pull it works.
Yeah, would you do that?
Yeah.